Okay, types of graphs. Bar graph. A bar graph is basically a graph that typically has a category on the x-axis and a number on the y-axis, and usually represents a mean, could be a mean value. In this case, we have a graph here at the top that shows different types of infectious diseases on the x-axis, and on the y-axis, the percent of all infectious cases. So this is a percentage. And you can see this bar has height of 17 because 17%, because 17% of all reported cases of infectious diseases were gonorrhea cases, right? Pretty straightforward. And the bottom graph shows the same data, but color codes it differently so that you can tell different kinds of categories. I think chlamydia, gonorrhea, and early syphilis are all sexually transmitted diseases. I don't know what that is. Campylobacteriosis and salmonellosis, I guess, is a kind of food poisoning. Maybe they're both food poisoning types. And then pertussis is a cough, other, right? Infectious diseases. So a bar graph is a really handy way of presenting data that you can quickly interpret. And you can see without a lot of work, chlamydia is by far more common than all the other diseases, right? It's really, really common. And gonorrhea is next. The other diseases are far less common, right? The bar graph shows a lot of information really quickly, really fast, really simple. Like them a lot. And there's this candy bar chart, which I really like. The candy bar chart tells us something about candy. On the x-axis, we don't have it labeled, but the picture shows us that we're talking about different types of candy bars. And on the y-axis, we have the amount of chocolate in each candy bar. And right off the bat, we can see that Hershey's milk chocolate has the most amount of chocolate in the candy bar, which to me makes it the best candy bar chart. Dot plots. Dot plots are very useful. We don't actually use dot plots a lot, but they can be very, very useful for representing the data because each point represents a particular data point. Each dot is a data point. So here we have shark length in feet ranging from, just probably like 9.5 feet to about 23 feet. So right away, when you look at the dot plot, you get an idea a lot more than, let's say if we had the bar chart of this, maybe we would just represent the mean shark length. Maybe it would be somewhere around 16. Say, okay, shark length on average is 16 feet. But having the dot plot tells us a lot more. First of all, it tells us the range of the data, the smallest shark to the largest shark. It also shows us that very few sharks are less than 10 feet, at least from the sample that was taken for this graph. And also very few sharks are more than 22 feet. Most sharks are clustered somewhere in between 12 and 20 feet. We can also see the sample size without actually counting them. It still gives us a rough idea. There were, there weren't 100,000 sharks measured here. There was maybe 30 sharks without counting them, right? Get an idea. And we can also see the distribution of the data, how the data are distributed. And we're going to talk about that a lot, data distribution. So we can see that there's sort of a peak of shark length somewhere between 12 and 14 and another one right around 16. Most of the data are clustered in here. It almost looks like maybe there's two humps, the two humps of the data. So as is explained here, these two dots are stacked because they represent two data points with identical values, right? So here we had 1, 2, 3, 4 sharks that were about 14 and 1, 2, 3, 4 sharks that were about 16 feet length. This might represent males and females or different age groups, right? So this right away gives us more information. Another way of doing this is by turning it on end. It's the same data, but just turning it on end. And we're going to see this represented in a couple different ways. But when you turn the data vertically and you just put dots, it gives you a really good idea of sort of how the data are distributed. Again, you can see that most of the data are clustered here between 12 and 20, but very few sharks, only one in this sample, were more than 20, and very few, one in this sample, were less than 12, right? So these are kind of extremes. Okay, dot plots. We'll be using those later. Okay, here's another example of a dot plot. So to make a dot plot, you first start by drawing a number line long enough to encompass all the numbers in the sample, and then show a dot over each position corresponding to each number. If more than one dot falls in the same position, they're stacked up. And in this case, we have an example of a dot plot of weekly test result averages. The girls are in green and the boys are in blue, and that helps us to see that about half the samples are girls, half are boys, and that also some of the lowest scores were from girls, but and then the scores from boys and girls were generally similar, right? So each dot represents the score of an individual on a test. Okay, the tastiest kind of chart here, the pie chart. Pie charts, well, pie charts are not always recommended. And that's because the human eye has a hard time distinguishing between like the size of a wedge when the wedges are pretty similarly shaped. That said, if you've got three categories of pie, let's say these are the number, you asked a bunch of people, what's your favorite kind of pie? And 26% of them said pumpkin, 46% said apple, and 28% said pecan. And you want to show that as a chart. This is a pretty effective way of doing it. It's good for showing proportions when there aren't very many categories, right? If you had 20 different kinds of pie on here, it might not tell the story very well. But if you've got three different kinds of pie, it actually tells you pretty clearly, okay, look, about half the people like apple, and about a quarter like pumpkin, and a quarter like pecan. So giving a general idea, it works all right and can be very simple. It's actually used a lot more often these days in genomic studies, where people are looking at the proportion of populations with different genotypes, and you'll see them a lot as like a subtype of another chart as you go on in science, if you choose to. Then there's the scatter plot. This is really the workhorse of statistics, the scatter plot. I'm sure you've all seen these. So this particular plot includes a regression line and an equation with an R-squared value. Note that the axes are labeled. When you talk about graphs, and you'll notice I try to remember to always do this. If I forget, remind me. But you want to start by pointing out the x-axis and reading the label. Station measurements of relative humidity. Okay. And it ranges from 20 to 70. That's your x-axis. And then you have the forecast of relative humidity. I think they made a typo there. Relative humidity ranging from 20 to 60. So here we have the independent variable was the actual measurement, and the dependent variable was the forecast measurement, right? And we want to see how well they correspond. How well do our forecasted measurements of relative humidity correspond to the actual measurements of relative humidity at various stations, right? Do they line up? If we have a perfect forecast, that would be a perfect relationship. All of these dots would be right on the line. and our R squared would be 1. But as you can see, there's some scatter. In other words, sometimes the station measurements are a little bit off, right? They're a little bit off. They're not always exactly the same. Here, our station measurement was about 25, but the forecasted measurement was about 30, right? And sometimes it's a little bit higher or lower than the predicted. So this line here is called a regression line. Each one of these points represents a measurement. And up here, what we have is y equals 0.586x plus 16.31. This is called the regression equation. The regression equation. You might remember this from other classes. So y, that's your forecast of relative humidity, your vertical axis, is equal to 0.586 times x, your x, station measurements of relative humidity, plus 16.31. That's the intercept, the place where if you continue this line along, it would intercept the y-axis at 16.31. Right? Your R squared is a measurement that tells you what proportion of the variation in the y variable can be explained by the x variable. In this case, about 80, almost 82% of the variation of relative humidity can be explained by the measurements of relative humidity. So that's a pretty good relationship. Not surprisingly, we're pretty good at forecasting relative humidity. So our forecasts are pretty close to the actual measurements. Line graphs. Now, line graphs are another way of showing that scatter. And in this case, the dots are omitted and it's like connecting the dots with just the lines. It's traced. Line graphs are often used for showing changes over time. So here on the x-axis, we have year from 1992 to 2002. And on the y-axis, we have the retail price of fresh oranges from 150 to 400. So time always goes on the x-axis, right? The variable of interest always goes on the vertical axis. And what we're looking for are overall trends or maybe cyclical patterns. So the overall trend, if you ignore all the ups and downs, just kind of squint at it, it would be sort of an increase in the price of fresh oranges over time. But as you can see, it varies. There's some variation, and we might wonder why that is. So there's, again, an upward trend in pricing over time. It could be simply reflecting inflation trends or more fundamental changes in the value of fresh oranges. And their regular pattern of yearly variations probably reflects some seasonal variation in the fresh orange pricing, probably because when the oranges are harvested, there's a lot of them, the prices go down, and then the prices go up when there aren't as many of them. Let's see, December, January, the middle of winter, the price goes down. Wait, there's that when they're harvested. This is sort of in the middle, the price goes up, and right around the start of the year, the price goes down. The price goes up, and it must be harvested around the time when there's the lower price, right? It's just a graph from the textbook, but I'm trying to make sense of it. Does that make sense to you? Okay, let's look at another one. We're more familiar with this one probably. So for this one, also from the textbook, but you've probably seen this before or some version of this. This is time again on the x-axis from 1958 to 2012. And on the y-axis, we have the monthly carbon dioxide in parts per million in from 310 to 400 parts per million. We've gone over this by now, but it's kind of dated already. You can see there's an overall upward trend, and there's also this seasonal variation. And you know, it's interesting that this seasonal variation represents the lungs of the earth, essentially, that the plants especially the huge forests in the northern hemisphere, they inhale or they take in carbon dioxide from the atmosphere and incorporate them into their tissues throughout the growing season, which is the summer in the northern hemisphere, the spring and the summer, and then exhale them when they drop their leaves and branches and bits of them rot, and that carbon dioxide is released back to the atmosphere in the northern hemisphere winter. And you might ask, well, what about the southern hemisphere? What's going on there? Yes, there is a lot going on there too, but there's just so much more land mass and so much more forest in the northern hemisphere that dominates this seasonal trend. It's pretty interesting. And you might also know that the some of the really important data for the CO2 in the atmosphere comes from Hawaii, from the observatory, one of the observatories on Mauna Loa. I'm not sure if it's open after that last eruption last year, but that's where some of this data comes from. So yeah, we're like part of it. Okay. Figures can be misleading. Figures can be misleading. So what's your first impression? If we look at this, okay, here we have time on the x-axis, right? 1900s to 2010s. And on the y-axis, we have number of murders committed using firearms. This is gun deaths in Florida. And we see this here where it says in 2005, Florida enacted its Stand Your Ground law. And then we see a decline in this line. So, but what's actually going on in this figure? This actually took me a while. Kind of embarrassed to say, it took me a while to figure this out. You'll probably see it faster. I think, all right, so the source here is the Florida Department of Law Enforcement. The Florida Department of Law Enforcement. Maybe they like this Stand Your Ground law. They think it's a good thing. And they want to believe, and they want you to believe, that having that law decreased the number of murders committed using firearms. But let's look over here again on the y-axis. Notice that 0 is at the top and 800 is at the bottom. So when this line goes down, the number of gun deaths actually goes up. This whole graph is inverted. The number of gun deaths actually went up after they passed that law. This was published in the news. Pay close attention. Okay, scales matter. How you stretch the axes and choose your scales can give a different impression. Here we have years again. We have the dots on the line from 1940 to 2000. Death rate per 1,000 for cancer. Not talking about guns anymore, just cancer. Kills more people anyway. So when you look here, you see, okay, the range of the data from the 1940 to around 2000 kind of stays right around 150, but it does seem to go up. When we look at it here, if we stretch these axes, we just basically stretch the graph. Instead of looking like a pretty flat line, now it looks like, wow, cancer went up. It really went up a lot over these years. Or if we look at it like this, instead of having 0, instead of starting our y-axis at 0, we start at 120 up to 220. Now, wow, we shrunk that range and expanded it, and it makes it look like, wow, there was a really big increase in cancer death. Oh my gosh, we should start really worrying about cancer. Like, why is it increasing? What's happening? What's going on? Is it all the processed food we're eating? It is, isn't it? Right? Here's maybe a more balanced way of looking at it, which is to just have a square graph that goes from 0 to 250. And it shows, yes, there is an increase in cancer deaths. Whether or not you think that's an alarming increase, That's up to you. It obviously seems like it's going up from, less than 150 to closer to 200 from 1945 to 1995. Does that mean we're more at risk for cancer? Or is it that other causes of death are less likely, or people are living longer and they're more likely to die from diseases like cancer, whereas they used to die from wars and accidents? I don't know. So a picture is worth 1,000 words, but there is nothing like hard numbers. Look at the scales. Moral of the story, look at the scales. Okay, histograms. I want to talk about histograms for a minute because we're going to be using these a lot, and I'm going to take this opportunity to tell you a little bit more about what they are. So let's say you just got the grades on a test from 15 students and you just write down all those numbers, 88, 48, 60, 51, etc. To build a histogram of the data, you first break the range of values into intervals or bins or classes, right? Chunk it up. You find the lowest and highest values, in this case, 48 and 97. So a fair size bin would be 10. So you can start the bins from 40 and stop at 100. So here we just make a little chart, scores and counts. 40 to 50, there's one, right? There's 148. There's one value that lands between 40 and 50, one. Between 50 and 60, there are two values, right? There's 51 and 60. Two values land between 50 and 60. Then how many values land between 60 and 70? 1, 2, 3, 4, right? Well, in this case, that's confusing because where do you put 60? In one bin or the other? Oh, yeah. Over here, it tells us include, not include, right? So in this case, 60 would not be included. So this bin includes 50, 51 and 57. It does not include 60. This is where 60 goes. Include is the square bracket, not include is the round parentheses. We've got 60, we've got 69, right? You see what I mean? You just count the number of values that go into each class, and then you make a graph of it. So you would say, here are your bins again, 40 to 50, 50 to 60, 60 to 70, etc. You just put that on your x-axis, 40 to 50, 50 to 60, 60 to 70, etc. You put that on your x-axis. You write scores, so we know we're talking about scores here. And on the y-axis, you write the counts. In this case, ranging from 1 up to the maximum of 5. So 1, 2, 3, 4, 5, right? You make your dots. And then you say, okay, from 50 to 60, we had 1. So you draw a line here. That's the first bar of your histogram. Not a bar chart. This is not a bar chart. This is a histogram, which is a bar chart of counts or frequencies, essentially. And from 50 to 60, we had two values, right? 1, 2. So we say 1, 2, draw your line here. From 60 to 70, we had 4 values. So we put your line here. From 70 to 80, we had 5. You go up 1, 2, 3, 4, 5. You draw your line at 5. From 80 to 90, 2. From 90 to 100, 1. You put all the bars right next to each other, and you can draw an imaginary line up and over these and see that it makes kind of a bell-shaped curve, This is your histogram. A histogram is just a chart of the number of times values occur within a particular interval. Does that make sense? Easy, right? We'll do some of that. And more. Now, this is just kind of just to show you. Here's a link to the R graph gallery where you can find the code and learn about making so many different kinds of graphs. All these beautiful graphs, amazing, beautiful graphs, even graph art with the code right there. You can copy and paste it from the internet, put it into your own R software and make a graph that looks amazing. And then you can modify it to work with your data. Handy tool, handy tool. Okay, so I'm going to stop the recording on that one, and I'm going to create another video to walk you through our exercise.